I will start off by introducing myself. My name is Jonsson. It's a picture of me, probably not totally recognizable because I have a hair on the other part of my head in that picture, but that is me. I studied applied physics and electrical engineering at Linköping University. I also studied at ETH in the same field, or more lean towards data science. I wrote my master thesis at NIRA within clustering of obstacles and clustering of information. And I also joined, after my master thesis, I joined NIRA as a systems engineer. I was recently taking over the role as product owner at NIRA. So I'm currently, and since 4 months ago, the product owner of the product packaging that we call Winter Road Insights. I can briefly mention as well, we have 2 additional product owners in the field of the cloud part, the RSI part. One is David Askenteg, who is the product owner of the automotive part, and one is Håkan Frank, who is the product owner of what we call road health. I will dig a little bit deeper into those fields as we carry on. Okay. So that was me. So now to the topic of what is NIRA to those who doesn't have that much insight in NIRA. So NIRA is a software company that is delivering software to the vehicle industry. So what we can say is that we currently have more than 55 million vehicles equipped with the NIRA software. And NIRA was founded actually in 2001, and it was a spin-off from Linköping University, and it was founded by Professor Fredrik Gustafsson. And the foundation was that the question was, can we estimate the pressure or detect pressure losses or actually punctures using only existing sensors in the vehicles? And the answer was yes. And then there was a regulation coming on European level and also in the US, and as of a few years ago also in Asia, that was regulating that, okay, all vehicles has to be equipped with pressure sensing or pressure loss sensing device. It could be a physical hardware, or it could actually be pure software as we do it, but it has to be that way. And that was partly to increase safety, but it was also to reduce carbon dioxide emissions. We have tested a lot of tires. Our specialty lies within the interaction between tires and the road surface. So we have tested 6,500 tires, and we have actually went back and forth to the moon if we add up the driven kilometers 20 times. So that's quite a lot of driving and testing and test data that we're working on. And as of today, we are 120 people, which consists of systems engineers. We also have test technicians who is planning and executing all these tests. They are the ones driving back and forth to the moon, basically. And then we have management as well. I can briefly mention we have operations, and within all markets, the headquarters is located in Sweden, Linköping. And we have operations in America, South America, Asia, and Central Europe. So we are more or less widespread all over the world. Okay, so we were basically sprung from the question: can we detect pressure losses utilizing already existing sensors? But in the recent years, the other question was, can we measure the properties of the road surface using already existing sensors? And the answer to that question is yes. So what NIRA and the business unit that I am working within is doing is by utilizing already existing sensors, which is the accelerometer and the ABS sensors, or actually how fast the tires are rolling. We create artificial sensors generating more insightful information, such as friction and such as roughness. I will come back to that a little bit deeper. And that is done using only software. So what we do is that we measure the unevenness of the road surface and also the potholes. So one very important question is how uneven is the road, basically. That is very important, and that we are doing by looking at how does the vehicle experience the road. So, for instance, how is it shaking and how is it transversing over the road, and we're detecting potholes basically to when you're driving down to it, you get some forces and fluctuations in some of the signals. So that's one of the important products that we're doing, and the use case of that is what we actually see here, that we can detect and quantify roads that are of this character, the character of not so nice to drive on, basically. We're also allocating resources within what we call tire grip indicator, or abbreviated TGI, and that one is used to measure friction. So it's measuring friction during normal driving conditions. And the theory behind the measurements is that this is what we call slip curve. So in the x-axis, we have the slip. Basically, the difference between if you apply no force, what would the tire roll, what speed would the tire roll at, compared to when you apply a force, you get it slipping a little bit. And on the y-axis, we have the exerted force between the tires and the road surface. Then we can plot the slip curve, and what's really interesting is the peak here. That determines how much traction force can you put down into the road, basically. So that one is really interesting. So what we are doing with the TDI is that we are pinpointing. I don't know if you can see my mouse, actually. I don't know if I can turn it on either. But the peak there up in on this graph is an interesting peak point. And what we're doing is to pinpoint that peak even during normal operations. So when we're even down at the current slip point, we are pinpointing the location of the peak friction potential. Just to show a little bit how this can be done in operations. So we're using several modules. This is called the cam circle. This is the name of it, and we can see that the red border is where the friction potential limit is. So basically, if you're deaccelerating at the red border, you're ABS braking, or if you're accelerating at the red border at the top there, you are doing basically burnout. And during those conditions, which normally doesn't happen very often, it's quite easy to measure the friction potential since it's basically related to the acceleration of the vehicle. What we can see in the middle picture in different colors is the operations of TDI. So we can see several modules. At 6 o'clock, the red ones, we can see the ABS module, for instance, which is using the ABS interventions to measure the friction. But we can also see that in the middle, close to where we don't have a lot of excitation into the system, we also have several modules operating and doing friction measurement, which is the revolutionary thing about TDI. And it's getting even more interesting when we're taking driving patterns into account. So as I said, when you're out in the red border, that's basically where you don't want to be. Then it's getting dangerous. Or if you're a racing driver, you want to be there, of course. But as a normal day-to-day driver, you want to be within that limit. And in the right circle there, we can see, okay, during a normal driving style, where are the friction information emitted? And we can see that almost all, more than 99% of the friction information is measured during quite low excitation, and that's the revolutionary thing about TDI. And that was quite a lot about the operations within the vehicles. So what NIRA is actually doing is that we are doing these calculations in the vehicles, and we are sending that to the cloud to be processed. So we are sending information from multiple vehicles up into the cloud, both roughness information, pothole information, we're sending friction information, and we're sending environmental information to build the most comprehensive insights in the cloud. And when we started that was prior to GDPR, but then the regulations came, which put a lot of questions into the agenda, basically. And still there are a lot of questions to be answered here. I mean, there are still practices being made as a law or interpreted in the Western world or European world. Most of how the cases should be judged is done through praxis. But this raised a lot of questions. So how can we, first question, is it personalized information that we are sending? Yes, partly. And the next question, how can we in a structured way manage this? And that raised a lot of interesting questions. So apart from the algorithms in the vehicle, we also have concepts for de-anonymizing the data, basically, so it can be used. This is actually, I think this is the real uprising field, the GDPR field. And what all this has led to, the research that we have put into the in-vehicle algorithms and coming up with a stable cluster and coming up with a concept that is compliant with the regulations within the European and the US. We have actually managed, as of last week, actually, get the first series vehicles transmitting data to us. So we are currently, as we speak, in the process of scaling up this fleet. So what we wanted to do is start slowly with a small fraction of vehicles, and we are currently scaling it up step by step. And what we can see there in the right is the first map actually generated over Germany showing friction information, which is from vehicles that has been produced in serious production pipelines. So what this basically means is that we do have the NIRA in-vehicle algorithms installed in vehicles that are rolling up production pipelines as we speak, and that is also connected to a GSM card that is transmitting this data to the NIRA backend, which allows us to make several map layers that is giving insights. In this case, it's a friction map layer. So last Friday we have some celebration online, of course, due to the new corona restrictions, but we were celebrating this, which is a huge milestone for NIRA, but also for everyone that can use this information as a next step. And that leads us into the really interesting questions, actually. How can this friction information be used in large scale to actually improve and change industries? So I want to highlight something first. So how do weather events impact roads? I guess a lot of the participants within this session is from Sweden. But so you basically know that, okay, during summer it's usually quite good friction, but then the snow comes and the friction gets quite bad, and that is common knowledge. However, most often people don't adapt the speed to the current conditions, partly since the current conditions are quite hard to judge by eye, but also partly because I mean they don't appear that often and you are not used to it. So, for instance, in the US, they had 6 million accidents each year, and approximately 21 of those were related to weather. And what we can say, I will show it on the next slide as well, but a lot of these accidents are actually due to not constant bad road weather conditions, rather to change in road weather conditions. And I can show that on the next slide. So this was research carried out in Sweden or for Swedish data. And on the x-axis, we can see how what's the percentage or how large of the fraction actually of the total mileage was driven on winter conditions. And on the y-axis, we can see how is the relative accident rate compared to bare dry road to good friction. And the colors, the blue one is hard packed snow, the yellow one is loose snow, and the purple one is black ice. So first observation is that, okay, if we get any of these winter conditions, the accident rate increases. That is most likely due to that the friction potential is lower. So if you need to brake, you have a higher probability to slide off the road. However, that is really what is really interesting in this graph is that, okay, if we have winter conditions, I mean, if we don't do any winter road maintenance at all, and we have winter conditions all year round, then the probability or the relative probability decreases compared to if you have it more seldom. And what's really more interesting about this research is that it's not connected to the first snow. So it's not like you get the first slippery conditions in October, then you learn for the whole of winter. So if you have varying conditions continuously over the winter, the probability of accidents don't decrease over time. It's rather constant over time. So basically, changing conditions increases the accident rate severely. So that means that it could be very dangerous to have very good roads and then suddenly that you get you judge the situations not in the correct way and get slippery conditions. So this is very important due to those parts that when you suddenly get slippery roads that you can be aware of it and either alert or either treat it. So that raises what can this large scale friction information do? So basically, the fleets that we are installed in are increasing in size as of every day, and they are scanning the whole road network continuously. So what could be done in that case is that it can actually pinpoint slippery conditions. So for instance, the exit in the north or in the upper left there is slippery, and the bridge is slippery, and the north traveling direction is slippery at a certain portion of the road. What could be done then is that that information could of course be transferred between the vehicles. And as most of you guys know, there are already slippery warnings, which is basically warning if the air temperature is between -3 and +3, a snowflake is appearing onto the dashboard, and then basically everyone ignores it. I mean, it's warning more often than when it is slippery. How our data is transferred in this industry is that it is basically replacing this false positive alert warning, which is -3 to 3, to where we can see a slippery road ahead. So we can say, okay, next corner will be slippery, or in 200 meters there will be slippery areas. Be aware, reduce your speed or increase your attention. And we can even show it on a map, as we see in the right-hand picture, where we see alerts being allocated over the road network. And based on that, you can imagine more use cases. You can imagine that, okay, we make this short detour to avoid this very, very slippery area. If you're going shopping or if you're going way ahead, you can actually select the route to reduce the probability of encountering dangerous conditions. There are huge opportunities for this data to be used to increase road safety. And it is available as of today. And it could also, as for the future, of course, be used to enable full-scale knowledge for autonomous vehicles. So imagine that you're developing an autonomous vehicle that you want to have some standard on. You want to say if there are obstacle or if anything is happening 200 meters ahead, we will most likely be able to avoid it. But that depends, of course, on your speed. And the relation between speed, distance, and friction is obvious. So to make any such judgment or such promise or such level of service agreement, the friction information is of huge importance, of course, to make a safe autonomous vehicle. And that information, of course, when you have the huge fleets, you will be able to provide it a full scan road that we see in the right picture. compared to today when there is very, very limited knowledge about the road conditions actually. We're also, this is my field, we're also working in enabling more knowledge within the road status for winter maintenance. So what is actually happening is that they are out salting and plowing the roads. Basically winter maintenance actions are being taken on the road network. And always when you do something, it is of high importance to know what was the outcome. I mean, you need to be able to judge, was it any good? Or how else could we be certain that we did anything right? So what's being done today is that there are several systems, of course, but there are more or less two types of systems that are being used. The left one, it's looking like it's from the 80s basically, but it's called a Coralba, and you're connecting that to the vehicle ABS system. And then you're traveling and you're doing an ABS brake, basically like TDI does when it is measuring friction to ABS brakings. So you estimate the friction through the acceleration, basically. So you need to install that one in a vehicle and then drive around and do ABS brakings according to a normal procedure at locations. Not very scalable, and it's quite hard to get any insights. You're doing point-wise measurements. The other one is that you are attaching, as in the background behind all the people. It's from Norway, this picture. The other one is that you connect a friction bag that is dragging a wheel behind it, basically, and braking that wheel and through that measuring the friction. And then you need to drive around the whole road network and scan it. What could be done with this type of connected information is what we have today is that we have local testings. So maybe someone is coming and driving on the road and doing ABS brake test, a Coralba brake test. What could be done with the NIRA data is that we can, of course, scan the whole road and pinpoint, okay, the main roads were very good in this case. We have good friction, we have green friction in the main roads. However, the exit lane wasn't properly treated, and we need to improve in the exits. And to be honest, in this case, usually you're driving in high speed, of course, in the main lane, in the main driveway, but you are most often not utilizing high friction potential. The only time you need to use high friction potential in the main driving line is if you need to emergency brake. And imagine that doesn't happen often, but when it happens, of course, you need that friction. However, where you are using quite a lot of friction actually is when you're turning and you're accelerating, the exits and entries to the highway. So there you need to have good friction, else you risk skidding off the road. And that is very important that could be pinpointed and visualized and of course improved on. When you get this picture, you realize quite fast that if you get this picture, especially several times, you realize quite rapidly that, okay, we need to improve our winter maintenance on the exits and entries of the road. And in this case as well on the bridge above the road to really provide safe roads. We're also looking into a quite interesting field since we are collecting several parameters that is related to weather. So basically around Sweden and around a lot of the Western countries, there are what's called RVIS stations. It stands for Road Weather Information Systems stations. And they are measuring, for instance, air temperature. They are measuring humidity, they are measuring surface temperature and so on. A lot of meteorological parameters. And if you compare that, a lot of these parameters are actually measured by the vehicle fleets as well. Maybe to a little bit lower quality, but in enormous scale. And for instance, these RVI stations, we do have 800, a little bit above 800 in Sweden. So we're getting point-wise measurements. So this vehicle fleet can actually, together with the friction, be used as mobile and moving weather stations and covering a lot of the gaps between the RFI stations. And therefore contributing to an even better picture regarding the development of the status of the roads. For instance, they could probably be used to find cold spots that are generated, dynamic cold spots. And those cold spots leads, of course, to local lower temperature, especially surface temperature, which means that it will freeze prior to other parts of the road. And that could also, of course, be detected by the friction. So by collecting all this data, additional insights could be generated where and when roads should be treated, and in the end also how they should be treated to optimize the material usage. Okay, as I said in the beginning, we're also measuring the roughness or unevenness and the potholes. And this is being done today with a quite expensive measurement instrument that is mounted onto a vehicle. So these measurement units are mounted to it's a laser scanning unit actually, so it's very expensive compared to the Coralba that is basically measuring the acceleration. So it's mounted to a vehicle, and then this vehicle are driving on around in Sweden and in every other country and measuring the road status or unevenness and pothole and cracking and so on. What we can do when we have vehicles, we can measure this continuously. So we can scan the whole road network more or less continuously and to a much lower cost. So what's happening here is that, okay, we're changing from annual measurements that is transversing to continuous measurements. And that enables more insights to be drawn. Apart from that, it is much cheaper than the expensive solutions. So in the bottom, we start to see seasonal effects. So can we use this continuous information to see seasonal effects that is affecting the road surface? And in the right, we actually see from a project that we had in cooperation with Largescale, that is the equivalent to the Swedish Road Administration, Trafikverket, in Netherlands. So we're looking what can we use this data for actually? And in this case, we see a quite short bridge that is passing some water. The water is actually passing under the bridge. And what we can see in the graph above is the measured roughness from the vehicle fleet. And what was really interesting, and no one actually really was expecting this, but what we could see was that, okay, we have quite stable roughness. It's the different colors are different parts of the road, but it's quite stable for this road. However, at a certain date, some of them jumped quite rapidly to a higher level, and that raised quite a lot of questions. But why did it increase suddenly? And what was happening here that I'm not into road construction, so this is very, very rudimentary description. But the construction under the road or the bridge construction was starting to fail. So it was starting to degenerate, and that could actually be detected. We also saw that we have what's called baffle plates. It's like concrete plates, and they were starting to shift, which causes the road to be very, very, very bad as well. So transferring from annual measurements to continuous measurements allows a lot more information to be seen in the road surface monitoring, but also will allow it to be found faster. Rather than roads failing and getting into an even worse state that is more expensive to repair, we can see it when it happens and act directly prior to really expensive things happening that has to cost a lot of money. Okay, that was what I wanted to to show on this Tech Tuesday. So we started off by looking into what could the in-vehicle, or what are we doing in the vehicles, and how is this information transferred to the cloud. And then we had some use cases within where this information can be used and improve both the road safety and road maintenance. I can just mention traffic management as well. I mean, a lot of cities are having dynamically allocated speed signs. So if the road is starting to get slippery, the speeds can be reduced and thereby increasing the safety of the roads. Okay, I actually landed on 31 minutes. I hope that it wasn't too fast, and I hope it was interesting as well. And thanks a lot for listening. If you want to come in contact with me, you can contact me on the contact details shown on the screen. And if there are any questions, I'm happy to answer them. I haven't managed to open the chat yet.
Yeah, please, everyone, if you have any questions, just write them in the chat and we will get to them right now. And thank you so much, William, for a very interesting presentation.
Yeah, thank you. I think we had one question from Aravinder Reddy. How does no friction in for? Okay, good. And the mouse was shown on the screen as well. That's great. Thank you, Richard. It seems like the presentation was quite clear.
Yeah.
Yeah, thank you as well, Richard. Thanks for joining.